Alrighty, welcome to week 8's Thursday 8 a.m. Section. I guess it's no longer at 8 a.m. because these are flipped videos, but if you're watching this at 8 a.m., congratulations, I'm very proud of you. As always, my name is Jaxford, and you can contact me any day. I'll try and get back to you as fast as I can at jbird@ucsb.edu. But before we get into topics of today, reminders. Midterm grades. We are still working on those. Those should be out to you guys by tomorrow, if not this weekend. You guys did just turn in homework 3, congratulations. But yesterday, sorry, I'm recording this early, so time's kind of non-existent. Homework 4 has been posted, and it's gonna be due March 9th. And in my opinion, homework 4 covers the material of this class that I found the most challenging and the most tedious of 15A. And I know that's hard to believe, but take it or leave it. So I do encourage you guys to start that early as possible. And if you do have questions about it, come in to, I know it's 8 a.m., and come in and see me at LSB at 8 a.m. on Thursdays. I do try and help out the students that do come. I think the ones that have been coming have found it useful. So otherwise, if you can't make it to that time, just send me an email if something really isn't clear about the homework, because I want you guys to be successful on the final homework, right, for this class. And final reminder, a little piece of advice. I kind of alluded to it as I was talking about homework 4, but there's going to be this really fast-paced switch for the material that is in the rest of this class, because it's covering topics that are a little bit more ECE oriented. And you guys are doing stuff that was very algebra and math oriented, and you guys dabbled in circuit realization, but this is where it really starts to get to stuff that you guys are going to cover in even more depth in 152A if you're a CE. I'm not sure if EEs are required to take that class, but that's digital logic design. And so this material is going to seem a little bit like overwhelming, especially because it's near the end of the quarter. Try to stick with it and get your questions in early. And if that's asking the professor, if it's asking me, either's good. You should ask any question. Dumb questions really don't exist in 15A. Or in ECE in general, actually. Anyways, course concepts we're going to go over today are gate delay and hazards. These are two things that are very, very real. I don't want to call them problems, but things that we deal with when we're working with actual signals passing through our gates. So let's talk about gate delay. We have been over how to change a Boolean expression or a function into a circuit using multi-level logic and AND gates and OR gates and NAND gates and NOR gates and XOR gates and all that fun stuff. Except the one thing about our circuits is that we haven't really been thinking about them in terms of time. We haven't really been associating a certain amount of time it takes to go from the input of your, let's just draw an AND gate here, to go from the input of your AND gate to get an output. So like, let's say we have like a change on your inputs going from low to high. If they both were doing that because it's a 2-input AND gate, then you would have also some sort of delay for your output to do the same thing. So signals don't pass through circuits instantly. This stuff takes time. And there's a certain amount of time from input to output, and that is what you call delay, or in fancier terms, propagation delay. So we're going to kind of understand gate delay through an exercise. And this exercise has us use a timing diagram. What a timing diagram does is it kind of shows the propagation of our input signals of a circuit and how they go through, how they propagate the circuit that they're attached to. So what I mean by this is that we have an exercise 8.10 that says draw the timing diagram for V and Z for the circuit. Assume that the AND gate has a delay of 10 nanoseconds, the OR gate has a delay of 5 nanoseconds. Okay, it tells us everything we need to know, but let's just look at the circuit itself and kind of like talk things through. we have our inputs W, X, Y. We have V, which I like to call, this isn't a formal term, but it's sort of an intermediate output because it's the output of our AND gate, except it's not our true output, which is Z, all right? And we also want to take into account that this AND gate right here takes 10 nanoseconds for any changes in its inputs, W and X, to be realized in its output V. And this OR gate right here takes 5 nanoseconds for any of its inputs, B or Y, to change and then have that change reflect on the OR gate's output, which is the output of our entire circuit, Z. Okay, so we talked time on this circuit, but things we should remember is that for an AND gate, when both inputs are high, W and X go high, that means that the output of that AND gate, V, is also going to go high. So we want to look for when both inputs, W and X, are high, or when V is equal to 1. And then for an OR gate, it's either inputs that would be equal to 1 or go high, which is going to give us an output of 1. And so to kind of give you guys an understanding, if either V or Y are equal to 1, C is also going to equal to 1. So we want to keep into account for this AND gate when both inputs go high, and then for this OR gate when either of its inputs go high. So for the timing diagram, let's take a zoomed out look at it. We have our inputs here, and then we have our intermediate output V here, and we have our final output of the entire circuit, Z, at the very bottom. And we have our timestamps in steps of 5 nanoseconds. I think the nanoseconds got cut off here, but this is in nanoseconds. We have timestamps of 5 nanoseconds that kind of break up each of the signals. So the initial signals of our inputs have already been drawn for us. They might be coming somewhere else on our PCB or coming from like another chip. We don't know. We don't know where they're coming from, but we see them on our timing diagram. And what I want to do first is find the signal propagation for V on this timing diagram. So let's just ignore propagation delay first off, and let's find out when V is going to be low and when it's going to be high. I can already see that W and X are high between 10 nanoseconds and 15 nanoseconds, and then they're also high between 30 nanoseconds and 40 nanoseconds. So that is going to be V, the output of our AND gate, being high for 5 nanoseconds. And then this width, oh, let's not zoom out. This width is going to be 10 nanoseconds, right? And then in all other cases, V is going to be low because those are the only two spots in which the inputs of that NAND gate are high, right? So if things were instantly changing, V would look like this. V would be like low, 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 high, low, 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 high, and then low again. Except we have to take into account propagation delay, right? And our AND gate has a propagation delay of 10 nanoseconds, all right? So let us use the dashed line here. And so when do initially we expect V to go high? Well, our inputs line up to be both high at the same time. And by our inputs, I mean W and X. They both line up to be high at 10 nanoseconds. So 10 nanoseconds from this starting point I've highlighted in pink is going to be when the output V actually goes high. So 10 nanoseconds from 10 nanoseconds is going to be here at 20 nanoseconds. So I'm just going to show you that that's where our signal actually goes high. So V doesn't go high at that place. It actually goes high for 5 nanoseconds because we remember that width we determined earlier, it actually goes high there. Now, let's do the same thing for when V also goes high, which is at this spot right here. And so 10 nanoseconds, because if you guys remember, that is the propagation delay set for that AND gate. 10 nanoseconds from this pink line on our timing diagram is going to be at 40 nanoseconds because 30 nanoseconds, or 30 plus 10 is 40. All right, so this is when actually our V output is going to go high for the second time. And it's going to go high for the width we determined earlier, which is 10 nanoseconds. And then it's going to go low again. So that is the actual signal realization. I'll say propagation. That's the actual timing of how V is going to respond to these inputs that change in this manner. All right, let's do the same thing, but for Z. And Z is now taking that signal we just determined, as well as how Y changes. And so Z is determined to be high by an OR gate. And so that means that either when V, this input right here, is high, or when Y is high, Z is also going to be high. So let's find those places in our circuit, and we'll denote all of this work done in green. So where does V or Y go high? Well, you can see that Y goes high for this entire length of time. And this is 1, 2, 3, 4, 5. 5 times 5 is 25 nanoseconds. So this goes high for 25 nanoseconds. Oh, that's a lie. This is 25 nanoseconds. And then also, we can see in that time, the second input to that OR gate goes high here, except it's already contained under this umbrella of the Y input, so we don't really care. But when Y is low, which is here, we can see that we just determined V to be high between 40 and 50 nanoseconds. So that is a width of Z going high a second time of 10 nanoseconds. Now, let's do the same thing where we take into account the propagation delay of that OR gate. So the propagation delay of our OR gate is 5 nanoseconds. And initially, Y changes at this 10 nanosecond mark. And then 5 nanoseconds from 10 is going to be 15 nanoseconds. So that means that Z is actually going high at 15 for what we determined earlier, 25 nanoseconds, or 5 time steps. So 1, 2, 3, 4, 5. Oh, are you not going to go straight? Sadness. Okay. And then it's going to go low again, right? But you might think, but it's high right here. So why wouldn't it just continue being high since it's an OR gate? And either of the inputs, if they're both high, will give us an output that is also equal to 1. You have to take into account the propagation delay as well. So from when V changes, that occurs at 40 nanoseconds. 5 nanoseconds plus, did I say 4 nanoseconds? I meant 40. But we can see that V changes here, and you can see that it goes from low to high. But because the propagation delay of our OR gate is 5 nanoseconds, we have to wait 5 nanoseconds before our output sees that and translates it. So that means that at 40 nanoseconds, Z is going to go low for a bit, and then it's going to say, hey, I got to go high again for that 10 nanoseconds width that we already determined. And we're going to put that out there, and it goes low again. So I'm going to try and clean this up so you guys kind of like see the whole big picture. What I just did is take an original circuit that was given to me, as well as the individual propagation delays of the gates in that circuit. And depending on given input signals and how they changed, I drew on this timing diagram how the outputs responded based on those initial propagation delays, as well as the widths of when the changes of our inputs correspond to a change in the outputs of those gates. So very cool. One thing to keep in mind, this is something that doesn't go away, unfortunately, in ECE. And I know, at least personally, timing and propagation and delays was never something I was comfortable with, but I kind of had to be, because you're going to see it in 152A, you're going to see it in computer architecture in 154, and most likely in a lot of signal processing classes you may or may not take. So that is all I have to say about gate delays. And the next thing we're going to move on to is hazards. And hazards is directly translated to delays because it has to do with time-dependent propagation. So a hazard occurs when your circuit has unwanted switching transients. And oh God, what does that even mean? Unwanted switching transients. Well, if we remember, just like outside of engineering, transient means temporary or fleeting. It means that it's there and then it's not. So you can kind of understand hazards to be outputs on our circuit that fluctuate when we're not expecting them to. So let me show you kind of like this process of discovering a hazard when you have a circuit. This is our circuit. We have two AND gates, an inverter, and an OR gate, and we have 3 inputs. So each of these gates have 5 nanosecond propagation delay, but we will ignore that for now because all I want to point out is that this circuit corresponds to A. Ooh, let's do it in green because those correspond to the AND gates. A, B naught, or B, C is what's going to set this output. Dang, my Apple Pencil just died. I'm going to pause the video for a hot minute. Ooh, memento. All right, my Apple Pencil is now charged. I swear I'm never going to get through a full video without something about my iPad screaming at me. But just to reiterate, we have turned this circuit that has 2 AND gates, an inverter, and an OR gate into a function, its corresponding function expression, A, B naught, or B, C, because you can see that those combinations make these individual AND gates go high. And if either of those go high, we have an OR gate that then can choose either of those inputs going into F, X, and Y. That will give an output equal to 1 in those cases. So I would just like to take away the fact that I made those guys yellow. Now, I'm going to see where there might be a hazard in this circuit by drawing its corresponding K-map. So if we remember, we had F is equal to A, B naught, or BC. And I have the corresponding K-map here, just to fill in the zeros for completeness. So the A, B naught term can be seen here when A is equal to 1 and B is low in the header that is denoted by these 2 zeros. And then the BC term is just this entire column because BC corresponds to 1, 1 when the header is BC. So cool. I mean, that's the K-map. That's what we're used to. This is a minimum function expression of this K-map. How you identify a hazard, though, is by circling the prime implicants in your K-map that could exist, but they don't, because they might be redundant. They might give redundant coverage. And the one hazard here can be seen. Oh, you were not supposed to be filled in. Yeah. Okay. Can be seen by doing this circling. So adding this term to this function isn't going to make it incorrect. If anything, it's just going to make it not a minimal function expression. But this points out a hazard because this is what we call, since we were grouping min terms here, or we were grouping ones, this is what we call a one hazard, where we are expecting an output that is consistently high, except I'm going to note that by consistently high, such that the output is 1, except instead we see a dip where it goes to 0. That is called a one hazard. So you can see by this prime implicate that we circled on our K-map that corresponds to the situation when our output is high and A and C are both high. So you can kind of tell that by A being high here and then C in the header being high there as well. And so that is when A and C are set to 1. And the hazard pops up when B changes, because in this grouping, we can see that it doesn't really matter if B or B is equal to 0 or equal to 1. Our function should still maintain being high. So when B switches from 0 to 1 or 1 to 0, we have a potential hazard in our circuit. So we're going to say that B goes from 1 to 0 in this case. And we're going to do the timing diagram in order to show why this is a problem. So we have A and C, which are high. And then we have B going from 0 or going from 1 to 0. So A being high looks like this, boom. And C being high, same thing. Is she just a straight line? Straight. Okay. And then B within the first, yeah, these are 9, or not 9, these are 5 nanosecond time steps. Within the first 5 nanoseconds is going to go from high to low. Okay. If propagation delay wasn't a worry, if things happen instantly in our circuit, what would this look like as far as the intermediate outputs X and Y and F? Well, we will see that, oh, I think she needs to be there for completeness, please. Okay, so if we remember, we have an AND gate that takes in A and B not. And so if B is going from, sorry, let me draw my input here. If A is high and C is high, and B is going from high to low or 1 to 0, that means that this inverter is going to, let's see, change that 0 to a 1. And so that means that this AND gate is going to turn on. So X is going to go from low to high. And then initially, both these inputs were equal to 1. And that meant that Y was equal to 1 as well, except when B goes low here, because we're doing a 1 to 0 switch on the input B, this AND gate is actually going to turn off. And then we're going to have Y do a high to low switch. All right, so if things are happening instantly, that means that X within the first 5 nanoseconds would be going low to high. And then Y would be going high to low. And in this beautiful world where we don't have to worry about propagation delay, we would see that F, because it's the ORing between the intermediate outputs of X and Y, would maintain being high, which is what we expect, because you could see that Y initially starts out high and then it goes low. But in that time when B switches at 5 nanoseconds, the output X takes over being high. And since F is just the ORing between X and Y, we don't have to worry. Now, let's take into account propagation delay. So I am going to, just for the time being, delete all of that fruitless work we've done. And let's remember the propagation delay of all of our gates, and it's all the same. And it doesn't matter that it's all the same because we're still going to run into problems. So we'll see that because the inverter adds an additional 5 nanoseconds before X can be realized, or the output of A and B, you can kind of consider this entire section of our circuit to take 10 nanoseconds. All right. Whereas Y, it only takes 5 nanoseconds because we don't have that extra inverter going into the inputs here, because it's simply B, not B not, if that makes sense. So let's do the response of X after this 10 nanosecond propagation delay when B switches. And so that looks like, let's use green because that's a calming color. At 5 nanoseconds, we have to wait an additional 10 nanoseconds. So that means that at 15 nanoseconds, stuff's going to start happening. And you remember that X is going from, apologies, let me think about this. It's going from low to high, right? And so initially, this was done kind of immediately at this section, but we have to wait a propagation of 10 nanoseconds because of that delay attached to that AND gate, and then as well as that inverter, because there's a combined delay of 5 plus 5 nanoseconds. Now, the output of Y, it doesn't take nanoseconds. It doesn't take 10 nanoseconds. It takes 5 nanoseconds because you only have this single AND gate here. And if you remember, Y is going from high to low. And so when B switches, Y starts out high, and then it waits another 5 nanoseconds because 5 plus 5 is equal to 10 nanoseconds. And we see that the output is going low here. Now, if you remember, the output of F is when you OR the two inputs X and Y. Those are the intermediate outputs from our initial AND gates. And OR gates are only low when both of their inputs are low. And you can see that the hazard is realized because, and I'll do it in red because hazards are bad. You can see that for 5 nanoseconds, that's this width, both X and Y are low. So that means that our F is not going to stay high, but rather it's going to do this. After this point, it's going to take a propagation delay of 5 nanoseconds every time. It's going to take a propagation delay of 5 nanoseconds because that's the delay associated with our OR gate on our original circuit, and it's going to dip, going from 1 to 0 and then back up to 1. And so instead of that original nice constant 1 value of our output F, we have this dip where we go from high to low for a little bit, then back to high. And this exact kinds of behavior in our output, when we expect to solely stay high, except we have a dip that goes low, that's called a static 1 hazard, which is no bueno. So in the next exercise, exercise 8.2, we're going to go over how do we make circuits that address hazards despite any sort of delay associated with the internal gates of the circuit. All right. So consider the following logic function. We've been through this. We got a bunch of midterms, and the first thing is part A, find 2 different minimum circuits. Okay, we know how to do that. That's just minimum SOP and POS, which implement F using AND and OR. Cool, POS and SOP. And then identify 2 hazards in each circuit. So let's do this out super quick. We had a 4-variable function. We're gonna move this guy right here. We have a 4-variable function, and we have midterms 0, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 are all set high. All right, so I just filled in my 4-variable K-map according to the midterms described in this original function up here, and we're filling in the zeros. All right, I, for completeness, should do this on my other K-map that I have over here. And why do I have it over here? Secrets that I will make very clear almost immediately. So I filled out our K-map, and now we want to find 2 different minimum circuits. So I'm going to first find the minimum SOP expression of F. I'm going to have these handy dandy little grouping squares to help me out. So I see that I compare these midterms together, and this set of boxes, the pink dotted, the purple dashed, and the orange solid lined boxes all denote the biggest pairings that we can do such that we have a minimum, the biggest groupings, I should say, because they're not just encompassing 2 midterms, but the biggest groupings that will give us a minimum sum of product expression. And if you aren't sure how this gives us a sum of product expression, feel free to ask me or go over my notes. I think it was week 5 about K-maps and how you find prime implicates and essential prime implicates within K-maps. So this grouping that I just did very fast realizes to this function below. And you can see each term in this function corresponds to the color as well as the textured outline of each of the boxes, because I do have one of my students that is colorblind. I apologize, but we're trying to do better. So that is a minimum sum of product expression for F, which was originally a bunch of midterms, right? Now, let's find the minimum product of sum expression using the same K-map. And that is just finding the minimum sum of product of F naught, or the complement expression of our function. And so that means we're going to be grouping zeros together. So we can do these 2 in the corner. We have the next level, which we can do this little wrapping. And then we can also group these 4 zeros in the corner here. And that is going to give us the, the sum of product expression for f prime. And if we remember, since f is equal to f prime, but simply complemented, you can apply an entire complement and then using De Morgan's law, filter it in such that you get this expression for S, where each of the terms that are underlined correspond to the groupings in the K-map above. Now, we already found our minimum 2 circuits using and OR gates for F, and using these K-maps, we want to find at least 2 circuit using ands and OR gates. The minimum circuits being these expressions here. We're going to use these K-maps in order to point out the hazards that each of these circuits possess. So already, this is a potential prime implicant pairing that we skipped over, as well as this is a potential prime implicant pairing that we skipped over. And I believe it wanted us to find 2 hazards for each circuit. And then also in this K-map, we can look at these zeros. So since we're grouping max terms together, and if we're circling zeros, that means we're looking at 0 hazards, which is when we expect a steady state of just 0, except we have a bump going to high. Just as bad, because any sort of unwanted behavior in our circuits is exactly that. It's unwanted. So we've identified 2 hazards already by just circling them in our K-map. And that is kind of it for part A. So part B and part C is finding an and or circuit for F, which has no hazards, as well as an or and circuit for F, which has no hazards. And so how do you make a circuit hazardless? Well, you're not going to have a minimum function expression or circuit realization of your original function, but you're going to have a robust and complete function expression. So that means that we're going to include and tack on those groupings that we made earlier that identified our hazards onto our function expression. So that first vertical grouping represents A naught, B, C naught, and then that second grouping, this one right here, represents A, B, D. So we will be doing the and or circuit, which should make you think in your head immediately, like if you see this on an exam or something, and or that means you want to start with an expression that is a sum of product, because you're doing AND gates first and then OR gates. So AND gates that feed into an OR gate. And what I have set up is something that you're going to be using next week, and you should learn to get comfortable with, which is kind of like a complete way of drawing a circuit. And I think it's really fun because it keeps things neat. I have all of my inputs here in groups of 4, as well as all the potential, not only when they're normal, but also their inverted versions. So these are all my inputs, right? And then I have all the AND gates that represent each of these terms here in the function that I've identified. And I'm just going to number them off 1, 2, 3, 4, 5. And so you can follow along all of these connections, because when we start having multi-gate and multi-input circuits, things can get a little messy. So I've numbered off everything, and we're going to identify first off, let's see, let's have this in pink, where A is in each of our terms. And so it looks like term 3 as well as term 5 have A. So I'm going to bring this input that is not inverted of A all the way down to gate number 5. And I'm going to connect that input here. And then it also is connected at the input of gate number 3. And I'm going to indicate that there is in fact a connection at this T crossbar looking thing with a dot. So I'm going to do the same thing now for A naught, and A naught can be found in terms 1, let's see, and 4. So bringing this down to gate number 4, and I'm going to connect the input. And then also it is the first input to our first AND gate. First of firsts, very nice. Same thing for B, which is found in this term here, as well as term number 4 and term number 5. So we're going to bring this line all the way down to the second input of term number 5 and connect it. And then also add in our connections for the fourth AND gate of our circuit, indicated by a little dot, and the second AND gate of our circuit right here. Connection. Okay. Looks like in our function expression, there is no B naughts. So we just leave that be and we don't connect this guy right here, but we can move on to C. And C can be found in our first term, our third term, and that is about it. So that means we're going to bring down C to the second input of our third term. And because there's only two variables in our AC, our third term right here, that means that there's going to be only two inputs to our third AND gate in this circuit. All right, just you knew that, but I was just reminding you. And so C is also in our first term here, and that's why I'm going to connect the second input of our first AND gate using a little dot to C. All right, C naught can be found in nearly all the other terms in this circuit except for the last one. So C naught is here, and C naught is also in term number 4. So I'm going to bring it all the way down to the final input of term number 4 and make that connection, as well as make it the second input connection of that AND gate right here. All right, moving on to D. We'll see that D is in the first term, the second term, and the final term of our function expression. And that means we're going to pull this all the way down to the final input of gate gate number 5. And then it is also going to be the final input of gate number 2 and gate number 1. And we indicate those connections with dots because there's a lot of crossings going on and we don't want anybody to get confused. So what I've just done is, by using this kind of like crossbar system of drawing my circuit, such that all the inputs are up here and then my output is over here, and doing the connections with little dots and a lot of right angles, I've drawn a successful circuit that is hazardless. So if there's delays associated with all of these AND gates or these OR gates, they are not going to form no combination of the inputs to these gates and the associated propagation delays with these gates are going to form a hazard. So we're not going to get any hazards because we've taken into account these extra terms that originally on our K-map above here, we identified our potential 1 hazards, right? So that is for an AND OR circuit that has no hazards. And we're doing the same thing with a OR AND circuit. And so kind of repeating what we just did, except now we're looking at our max terms. And so originally we're going to add on the product terms to our F naught expression. And this hazard that we identified here, this 0 hazard, that is covering the term, let's see, A, B naught, C naught. And then the second one identified here is A naught, B naught, D. So when you translate this to the product of sum of F, because I just wrote the product terms for F naught, that's going to translate to the additional terms A naught plus B plus C, as well as A plus B plus D. All right, so this is a function expression using and OR gates that will have no hazards. And we're going to bring that down here and do the same kind of connection game, except we are now using an an OR AND circuit, right? Because we have OR gates here and we have an AND gate that connects all the outputs of those OR gates to our final function output. So where are A's in this circuit? I'm going to try and do this relatively quickly because it's kind of the same thing as before, but they are in our, let me label these first for you guys. So that is 4, 1, 2, 3, 4, 5. A can be found in the input of the 5th AND gate, can also be found in the input of our 3rd AND gate, as well as the 2nd. We make connections. All right, A naught can be found then in our first term here, as well as our fourth term. So that means we're going to bring it all the way down to OR gate number 4, connect those guys, and also bring over the inputs of our first OR gate, because A0 is in our first term. And then we're going to be moving on to B, and B can be found in 4 and 5 only. Very interesting. We'll bring that down to the 5th OR gate and connect the second input of our 4th OR gate and make a connection with a dot. And then B0 is, again, not anywhere in our circuit, so we're not going to touch that input. We're going to move on to C, and C can be found in 1, 2, and 4 terms. So that's going to be 1, 2, as well as 4 is lining up. And that means I'm making connections here and here. And C0 is only found in the 3rd term here. And interestingly enough, already the 3rd AND gate, or sorry, OR gate is already done. And then we move on to input D, which can be found in the 1st term of this product of sum expression for F, as well as the last term in this POS. And so I'm going to bring that input all the way down here, make a connection, and also connect the final input of our first OR gate with a dot. And then D0, you can see already that this is the final input to one of our OR gates that needs some love. And in fact, that final input should be D0. And all is right in the world when we make this connection. And there you have it. We have an OR AND circuit that if there were propagation delays associated with each of these gates, there would be no hazards. So no combination of inputs A, B, C, D, and their inversions would give us any sort of 0 hazards or 1 hazards. So that is all I have on this week's section. It was a lot kind of going over these examples, and I might have gone fast, but if you're confused at all, ask questions or go over these notes. They'll be posted on my Gauchospace folder as soon as I can get them up. So I wish you the best of luck, and I hope you have a great rest of your day. All right, bye guys.